Hi, this is Chandrakant here. Today we are going to discuss the third part of the transient analysis. In third part, we'll discuss the inverse Laplace transform. And if you have not read the first two parts, then please go back to the first two parts and learn the basics of your transient analysis, then come to this part. So let's start. So inverse Laplace transform is done by looking at the transform pair table. We do not directly find the inverse Laplace transform, or maybe it would be cumbersome to do that. So instead we partial fraction, or we can manipulate the algebraic expression into a potential, or you can say viable Laplace transform pair in time domain. So to do that, we first expand that is your algebraic expression, and that expansion is called the Heaviside expansions, that is popularly known as partial fraction. So three cases arises in the denominators in a algebraic expressions. Case 1, that is non-repeated terms, like 1 upon s plus 1 and s plus 2, let's say. Then repeated terms in denominators, like s into s plus 1 square. You can see that the terms s plus 1 is repeated. Third case is the purely quadratic terms. Purely quadratic terms, like 1 upon s into s plus 1 s square plus s plus 2. So we'll discuss one by one how to partial fraction it. So first case, let's say one expression is x of s we found by with the help of Laplace transform, that 2s plus 3 s square plus 2s s square plus 3s, okay, then 2. So as usual, 2s plus 3, this is not a, in the denominators it's not a purely quadratic. So what I'll express in the multiplication of two first order terms. So you can easily see that this is s plus 1 into s plus 2. So then we need to partial fraction it. So because there are two terms, so I'll do a constant s plus 1 plus b s plus 2. Then I need to find the a. See, whenever there is a coefficient, you can that is your degree of numerators is equal to degree of denominators, then before writing in this form, first you divide the terms, so that divide the denominator with the divide the numerator with denominators, so that the remainder becomes the less than, at least 1 degree less than the denominators. I'll show you later on. So here you can easily find out the way you have done in your intermediate courses, but wherever required, we can use that equating the coefficient of left hand side and right hand side here, and you can easily calculate A by another technique, that is just Heavisides have invented that is multiply s plus 1 both the side. So A equal to, we normally say x of s into s plus 1 evaluated at s equal to minus 1. So what happens, you see here, when I multiply this term and this term with s plus 1, so s plus 1 here gone, here is the s plus 1 gone. So what happens, so only a will be here and this term vanishes when I put the s equal to minus 1, because this term becomes 0. So I can write 2s plus 3 upon s plus 2 evaluated at s equal to minus 1. So minus 2 plus 3, then minus 1 plus 2. So 1 upon 1, which is 1. In similar fashion, you can find out b equal to, directly you can write 2s plus 3 multiply s plus 2 both the side, then evaluated that term with s equal to minus 2. Whatever you are multiplying, just ensure that s value has to be values to be evaluated in the term. Here I have multiplied s plus 2, so I will evaluate at s plus 2 equal to 0, which implies s equal to minus 2. So when I evaluate it, so what I get, so 2 into minus 2 plus 3 minus 2 plus 1, that is minus 4 plus 3 upon minus 1, that is minus 1 upon minus 1, 1. So finally your x of s becomes 1 upon s plus 1, 1 upon s plus 2, right? So you can easily also check that, see, 2s, then 2 plus 1, 3. So now it is in the standard form of, to get into the directly the inverse Laplace transform. So you know, you can easily find the Laplace transform, inverse Laplace transform of x of s, that is e raised to the power minus t plus e raised to the power minus 2t. And as usual, all the in the network theory we are considering the things are causal and LTI. So you can write u of t or t greater or equal to 0. So first of all, you need to learn the Laplace transform pair table. Next case, we go to the second case, that is repeated terms, like x of s is equal to s plus 2 upon s plus 1 square into s plus 3. So in this case, number of terms are 3. So because though it is repeated, so it is the 3 terms. So you need to write like this: s, a single non-repeated term 1, s plus 3, then plus b, all constant, okay, b s plus 1 plus c s plus 1 square. For example, if s plus 1 q, then you can extend another term also. So whenever the there is repeated terms, so we can write in this partial fraction way, that is for each repeated terms we have to add one term. So same way, but remember, you can directly found this one and this one, but not this one. Like we multiply, let's see a, you can easily multiply s plus 3 both the side. So s plus 2 s plus 1 square evaluated at s equal to minus 3. When I put the s equal to minus 3, these terms become 0, this term become 0, and we have only a. So minus 3 plus 2 upon minus 3 plus 1 square. So ultimately you get minus 1 upon 4. You can directly find out the c when I multiply s plus 1 square both the side. So s plus 2 upon s plus 3 evaluated at s equal to minus 1. These terms become 0. When I put the s plus 1 square, this will be, the one term will be here, that is s plus 1. When I put the s equal to minus 1, this a and b terms both 0. So put the values s equal to minus 1. So c equal to s equal to minus 1. So minus 1 plus 2 minus 1 plus 3. So what I get? Obviously 1 upon 2. Then coming to the b. B, suppose you ask me that, sir, I can multiply s plus 1 and find out the, when you multiply s plus 1 both the side, you have here s plus 1. So you cannot reduce this term to 0. Okay. So what we'll do here, because already the another Heaviside way is there, like differentiating both the side by multiplying s plus 1, but we will not do that. Okay, we'll do, because we have already find out the two terms easily. So just we'll do a coefficient matching of both the side, right? So let's see, we match the coefficient of s. So we have s plus 3, then s plus 1. So just write. So I can write s plus 1 square into s plus 3 equal to s plus 2, which is equal to same s plus 3 into s plus 1 square, then a into s plus 1 square and plus b into s plus 3 into s plus 1 and plus c equal to s plus 3. So what I'll do, I'll equate the coefficient of a constant term. So when I equate a constant term, here I got the a, then plus that is 3b plus 3c, right, equal to, here equal to constant term is your 2. Okay, so 3b equal to 2 minus 3c minus a. Okay, so 2 minus 3c, so c we have got, that is your 3 by 2, then minus a, so minus minus plus 1 upon 4, that is 4, then 8 minus 6 plus 1, which you get 9 minus 6, that is 3 by 4, and what you will get? So b equal to 1 by 4. Ultimately your x of s becomes minus 1 upon 4 upon s plus 3, then plus 1 upon 4 upon s plus 1, then plus half upon s plus 1 square, right? So you can easily find out the inverse Laplace transform in the time, that is your time domain function, 1 upon 4 e raised to the power minus 3t plus 1 upon 4 e raised to the power minus t, and you can, you know this with t e to the power minus t, so half t e to the power minus t for t greater or equal to 0. Okay, second case is clear. We'll next move to the pure quadratic form. So third case is the pure quadratic. So for pure quadratic term, consider this example x of s. So for first order factors, as usual, a upon s plus 1, because it is a second order and it's pure quadratic, we cannot have two first order factors, so we'll write like this: b s plus c upon s to s square plus 2s plus 5. Now we can find out what are the a, b, c, and finding the a is very straightforward. A equal to, just multiply s plus 1 both the side, so h upon s square plus 2s plus 5 evaluated at s equal to minus 1, right? So when I put the minus 1, then 1 minus 2 plus 5, so minus 1 upon that is your 4. So then multiply a square plus 2s plus 5 both the side, we have s upon s plus 1 is equal to s square plus 2s plus 5 upon s plus 1 a plus bs plus c. So if I put s equal to 0 here, so s plus 5 upon 1, so 5a plus 0 plus c. So c is equal to 5 minus 5 of a, that is 5 minus and minus plus 5 by 4, right? So your c will be the 25 upon 4. So there is a mistake, actually it is s upon 4. From here I have considered as a 5, so in fact it is 0. So c equal to 0 minus 5a, that is 0 plus 5 by 4, so 5 by 4. Now next is the how to find the v, right? Very simple. You can equate the coefficient of a square s square, right? So you can see the coefficient, this side is the right side, a into a square plus 2s plus 5 plus bs plus c into s plus 1. So coefficient s square, here coefficient is the a and here is the b, a plus b. Here the coefficient of square is the 0, because 0 into a square plus 1s plus 0, like that. So it is 0, so your b equal to minus a. So minus a means that is 1 upon 4. So finally we have x of s is equal to minus 1 upon 4 upon s plus 1 plus bs 1 upon 4s plus 5 upon 4s upon s square plus 2s plus 5. Still it is not in the standard form to, that is, I mean second term is not in the standard form for lookup table. So we need little manipulations. So it is as usual 1 upon 4 upon s plus 1 plus take common 1 upon 4 s plus 5 and this term is not there. So here a square plus 2s plus 1 then 4. So I want to make a standard form minus 1 upon 4 s plus 1 plus 1 upon 4 s plus 5 upon s plus 1 square plus 2 square. Still it is not in the standard form of cos or sine. 1 upon 4 1 upon s plus 1 plus 1 upon 4 s plus 1, okay, plus 4 upon s plus 1 square plus 2 square. Next, keep continuing. 1 upon 4 upon s plus 1 plus 1 upon 4, okay, s plus 1 upon s plus 1 square plus 2 square plus half into 2, okay, s plus 1 square plus 2 square. Now you can write the x of t minus 1 upon 4 e to the power minus t plus 1 upon 4 e to the power minus t cos 2t plus half e to the power minus t sin 2t for t greater or equal to 0. Okay, hope it is clear the process. Now we'll move to the transform of elements. First we'll consider the resistors. By Ohm's law, V equal to, I mean t, time domain, it, and Vt equal to, so taking the Laplace transform of both the side, we have Vs is equal to Is into R. So Vs upon Is is equal to R. Okay, so in Laplace transform domain I can write same R. Okay, normally it is written it is drawn as a box, Vs and Is. This is the very simple. Then we'll move to the inductor. Second is your inductors. We know that this is a inductors. We have a Vt and we have a It, and this is the inductance. In time domain, a dynamic equation is written as Vt is equal to, and let's say some initial current IL 0, Vt equal to L DIL DIT, okay, DIT upon dt. Take the Laplace transform of the both the side. So V of S is equal to L, Laplace transform of differentiation is the S Is minus I0. So LS IS minus LI0, right? So this is the voltage transform equation. LS IS is the due to the impedance, and this is the due to the initial current, that is the voltage that is a initial voltage transform due to the initial current. So it's just a equation or KVL we have written. So how can I write this in a symbolic way? That is, the transform becomes a box to represent LS. This is your IS and this is your VS. Oh, sorry. So this is a voltage transform due to the initial current through the inductors, and which is the in a direction is same as the voltage source. So plus minus L I 0, 0 minus or 0 plus, no issue, you can write. So that's why I have written I0, that is the initial current, and this LI0 is the voltage transform of the initial current in the inductors. You can also find out the transform of the that is your current transform, just equate with the IS. So LS IS is equal to VS minus VS plus LI0. So IS is equal to VS upon LS plus I0 upon S. This I0 upon S is the current transform, that is the transform of the initial current. This is the transform of the voltage due to the initial current. This is the transform of the current due to the initial current. So you can simply write this is your IS plus minus V of S, this is your LS, and this is your I0 upon S. You can easily find out from this diagram or this circuit by using the Norton's theorem. From this you can got by the Thevenin, from this you can got it via Norton. So one important point I want to say you here, see the direction of the voltage positive terminal. There is no issue, absolutely no issue when you do the current transform, because the direction of current is coincides with the direction of current transform. But voltage transform, you see the voltage source is connected or transformed in such a direction or such a polarity that when current flows through the positive, because current will start flowing through the positive from the positive terminal, so that will be aligning with the initial current. So this is the transform of current, and this is the transform of the inductors with a voltage transform. This circuit is for the voltage transform, and this equation is the voltage transform, and this equation is the for the current transform. Now let us move to the inductor. I mean capacitor. Inductor we have done, so capacitors. Sorry, IT na, IT time domain VT. So from dynamic equation we know that IT is equal to C dVt upon dt. Taking the Laplace transform of the both side, Is is equal to C S Vs minus C V evaluated at t equal to 0. Right? So you can write this equation, right? And the voltage, initial voltage is this. In this, that is, we have a V0 plus or V0 initial voltage across the capacitors. So this current can be written as like this, 1 upon Cs, then a current in this direction, that is C V0 Vs, and this is your Is. You just put a KCL and you will easily got it. Now we want a voltage transform. As usual, you do just equate with the Vs equal to Is upon Cs plus V0 upon S. That means whenever you have a initial voltage, so you can easily see that will be a impedance of 1 upon Cs, then a voltage source opposite to the applied voltage source due to the initial voltage across the capacitors, which is V0 upon S. This is the voltage transform in Laplace domain. This is your Is, this is your Vs. This equation govern to the voltage transform and this equation govern to the current transform. Okay, after learning all the transform, let us go to the circuit. Okay. Let us, we have been given a circuit of R. Let's say we have a C, then we have another R. Let's say it is R2, this is R1. Then let's see equal to, for simplicity, 1 farad. Inductor, let's say 1 Henry. Initial current, it has been given as the let's say 1 ampere initial current, and initial voltage across, so I'll write like this. This is your Vc, this is your IL. So initial voltage Vc0 plus is equal, let's say 2 volt, IL 0 plus, let's say equal to 1 ampere, and altogether we have a step voltage here. Let's say it is 1 volt, right? So question is whether you should go first write the dynamic equation, then use the transform. So the biggest advantage of the using the Laplace domain in the circuit is in the circuit itself you apply the transform. So see, one by one I will be doing. I have left the value of R1, R2. Okay, R1 let's say 2 ohm, R2 let's say 1 ohm. Correct? And remember the initial voltage. Okay. So symbol remains same. So 1 volt. What is the Laplace transform? A step input 1 upon S. This is a 1 volt. So 1 upon S. And resistors remain resistors. Don't put here ohm, okay, just values. Then come to the capacitor. It's an important point now coming. First you have a box here. The value is 1 upon, because I am applying the voltage transform, already we have seen that is the 1 upon Cs. C I have taken 1, So 1 upon Cs become 1 upon S, right? Then initial voltage with this polarity is the 2 volt. What is the transform of the voltage? Transform voltage will be the V0 upon S, that is 2 upon S. And that is the most important one is the what is the polarity. Polarity will be same as it was initially. So initially top node is the positive, bottom node is the negative. So this is positive, this is negative. We have done with the, that is your capacitors. And what is the VC? VC is the this terminal and this terminal. This is your VCS. Now R2 simply 1. Current I am transforming into the voltage. You can do the either current or voltage. Okay, so I'll do here voltage transform for the inductors. So the works will be the LS. LS is the L is equal to 1. So 1 into SS. And voltage transform I have told you. What is the transform? L I0. So L is the 1 Henry, I0 is the 1 amp. So L I0 is the 1. Okay. L I0 is the 1, and the polarity is the will be the voltage polarity of the inductor voltage transform will be the in a such a way that when current flows from the positive terminal, it aligns with the current actual current direction. So obviously this will be positive, this will be negative when current flows from positive terminal towards the circuit. So current exactly aligns the, because this is the direction, so this aligns in the same direction. Okay, now you have, and this is the current your ILS. Now see, I have converted a complicated circuit into a simple algebraic expressions. Now as usual, either you apply the node equation or that is KCL KVL, that is means either KCL means your node equation, KVL means your loop equation, and then find either VCT, VCS or ICS, whatever you required. Then it will be a algebraic expression like AS plus B upon AS CS square plus DS plus C type, then partial fraction it, then take the inverse Laplace transform, then you will get the whatever the result. This is the way. Another way is the do the write the differential equation as usual, find the characteristic equations, then complementary functions, then particular integral, then arbitrary constant. That I have done in my second part of the transient analysis video. So in the next part of the transient analysis, we will do some example and then application part and examples, and wind up with the some gate questions, right? So hope you are learning from my class. So if you have not gone through the part 1 and part 2, so I request you to understand this. First you go to the part 1, then logically part 2, then part 3, then after part 4. Okay, see you in the next video. Till then, take care, bye bye. Please subscribe and tell your friend to subscribe to learn the things which will be helpful for your competitive exam.